So I'd like to just discuss an interesting relationship between our differentiation, our binomial coefficients, and our factorial notation that we've discussed. Over here, I've differentiated function x, which is x to the power of 5, down 5 levels. The first derivative is 5x to the 4. Second derivative, 5 times 4, x to the 3. I've deliberately left it like that rather than writing 20 because I want to show the relationship with factorial notation. Because if you keep differentiating down, 5 times 4 times 3, x squared, 5 times 4 times 3 times 2, x to the 1, 5 times 4 times 3 times 2 times 1, x to the 0, x to the 0 is 1. Then this is just equal to 5 factorial. If you differentiate down x to the 5 levels, you get 5 factorial, which is quite interesting. I've also expanded out 1 plus x to the power of 5 here because we are talking about our binomial expansion here and our coefficients, which is just expanded out the normal way. And I've replaced it with those numbers out of Pascal's triangle because 5c2 is equal to 10 and 5c3 is equal to 10 and 5c4 is equal to 5 and so on. What I'm trying to show is some relationship between these derivatives and the binomial coefficients, well, actually the actual expansion of 1 plus x to the power of 5. Now, it starts off, if I turn this around, it might be a bit easier. So if I rewrite it going from the other end, it's still equal, but x to the power of 5, which is my original function, plus 5x to the power of 4, plus 10x cubed, plus 10x squared, plus 5x plus 1. So I've just written it the other way around. I can see straight away that the first term is equal to my function that I've declared to be function x. I can also see straight away that my second term is equal to the first derivative. So that's nice. That's equal to f dashed of x, the first derivative. When it comes along to the third term, I'd like it to be equal to the third derivative of x, but it's not because that's 20x cubed and this is only 10x cubed. So I need to divide by 2, which I'll just put in there and I'll see how I go. This next one, I'd like that to be the same, but it's not the same as here, our third one along, because that says 10x squared, but this would be 60x squared. So it's the same as that should be the second one. It's the same as the third derivative, only divided by 6. 60x squared divided by 6 would give me my 10x squared. Once again, I'd like this one to be the same as this, 5 times 4 times 3 times 2, right? So that's 120. I'd like it to be the fourth derivative, but 120 is nowhere near 5. I'm going to have to actually divide by 24 to make it the same. And finally, I would like this to be the same as my 5 factorial, my last one here, my fifth derivative, which is equal to 5 factorial. But in order to get 1, I need to divide that 5 factorial there by 5 factorial. And that makes me think, if that's 5 factorial, and these numbers 2 and 6 and 24 are something that's familiar, 5 factorial, 4 factorial, 3 factorial, 2 factorial. Would the pattern work if I continued? Yes, 1 factorial, 0 factorial. It would work if I wrote f of x over 0 factorial plus f dashed x, the first derivative, over 1 factorial plus the second derivative over 2 factorial plus the third derivative over 3 factorial plus the fourth derivative over 4 factorial plus the fifth derivative over 5 factorial. So what I've tried to show here is that there's a relationship between the actual expanded terms of the binomial and also the derivatives, and also inbuilt into that a relationship with our factorial notation that we've been learning.